Hi everyone. So hopefully you've seen the MIT jumping wire video, so you can get a sense of what direction the magnetic force ends up pointing due to a moving charge moving inside of a external magnetic field, as well as that Khan Academy video that kind of gives you more of an intuition as to what the magnetic force depends upon. So I'm going to now work through giving you the equation and talk about how to calculate the magnetic force, where the next video I'm going to show you is how to apply the right-hand rule so you can determine the direction of the magnetic force. All right, so let's just talk about this. So let's see. If you have a moving charge, and I'm going to take this out right now, and I'm going to put it inside the magnetic field here, because the second the moving charge goes into the magnetic field with some velocity, the magnetic force, how you calculate it is, so let's say it's a charge Q. It's going to be the magnetic force is going to be the charge Q itself multiplied by V, the speed of the velocity of the charge, cross B. So that's a cross product of the velocity and the magnetic field vector, which you guys know the cross product is just, if I wanted to take just the magnitude, we've done this with torque, before in other quantities. So it's just the magnitude of the velocity times the magnitude of the magnetic field times sine of theta, where theta is the angle between the magnetic field vector and between the velocity vector and the magnetic field vector, which is exactly like we've done with cross products all the time before. So yeah, these are, I mean, both of them are fine ways to calculate something. Another way you could, get this expression yourself, but, just in case, what if we had instead, so let's use again the same thing here. Copy, and I'll paste you here. So again, but instead of this wire, so again, instead of this right here, let's say instead I had a wire with a current moving this way. So the current was moving this way. So there's the current I moving that way, and it's in that magnetic field. Well, and then let's say we're talking about a length between here and here. So we're going to talk about that length there. So it'll be a length L. Okay, well, let's see. So to calculate this magnetic force, it's the charge multiplied by the velocity, we'll say the speed, times the magnetic field, times sine of theta. But wait a minute, I don't know the velocity, and I don't know the amount of charge, because as a current, I got multiple charges moving through the wire here. So what the heck, how do I do that? Well, velocity is just distance over time, right? Velocity, or speed, is just the distance over the time. And let's say the distance that we travel is L. So the distance we travel is L. So that would give me the magnetic force is the charge multiplied by L over T times the magnetic field times sine of theta. And so, okay, all right, well, let's, I'll take the T and bring it over here. So I'm going to take the T, take the time, put it over here. So that'll be FB equals the amount of charge divided by, let's make that a delta T, the change in time, divided by the change in time. And let's see, multiply it by L, and multiply that by B sine theta. And wait a minute, I know this. I've seen this before. Charge over the amount of time, the amount of charge over the amount of time it takes. So the rate of change of charge, that's current. That's current. So really, this is just going to be FB is the current multiplied L multiplied by B times sine of theta. Or better way to write this, easier to remember, is that it's Bill, like Kill Bill. Yeah. So this is the magnetic field. This is the current of the wire. This is the length of that wire, how big that wire is. So, and then this is, again, the angle between the current, whatever direction the current is moving, and the magnetic field vector. So there you go. All right. Hopefully that helps. Go watch the right-hand rule video now, and I'll see you later. Bye.